Most of the electrical infrastructure that powers our homes and cities runs on alternating current. Alternating current, or AC, is an electrical flow that rapidly reverses its direction many times every second, making it incredibly efficient for long-distance transmission. If you hook up a standard direct current, a steady flow in one direction, to a capacitor, it acts like a temporary storage tank. The capacitor, which is simply two metal plates separated by an insulating gap, quickly fills up with charge and then acts like a solid wall, completely blocking any further flow. This visualization shows what happens when we switch to alternating voltage. The physical wall is still there, and the electrons never actually cross the gap. Instead, the alternating pressure keeps the electrons rhythmically vibrating in place on either side, creating a continuous pulsing flow of energy. But watching this pulse reveals a bizarre phenomenon, a phase race. The physical flow of the electrons actually reaches its maximum speed before the electrical pressure pushing them, the voltage, hits its own peak. The capacitor plates are constantly filling up and emptying out. Because the current is driven by how empty the plates are, this rhythmic charging cycle physically forces the current to stay one step ahead of the voltage wave driving it. This animated diagram shows a pure capacitive circuit. At any given moment, the instantaneous voltage across the physical plates of the capacitor has to perfectly match the alternating voltage coming from the source. The total amount of charge packed onto those plates is determined simply by multiplying the capacitance of the plates by that instantaneous voltage. As the voltage rises and falls like a sine wave, the stored charge follows along exactly. But we want to know the current, which is the time derivative of that charge. A derivative is a mathematical tool from calculus that measures the exact rate of change of a quantity at a specific instant. When we calculate the derivative of our sine wave, we get a cosine wave. And a cosine wave is mathematically identical to a sine wave that has been shifted forward by exactly 90 degrees, or plus pi over 2. That plus pi over 2 factor is the mathematical fingerprint of a current lead. The electrons are literally flowing a full quarter cycle ahead of the voltage. The math proves that the maximum rush of electrons doesn't happen when the voltage is at its highest. It happens exactly when the voltage is crossing zero and changing the absolute fastest. This animated diagram shows a phasor model, which helps us visualize that math. A phasor is a rotating vector used to track both the peak value and the specific timing of an oscillating wave. Here we have one vector for voltage and one for current. As the system oscillates, these vectors rotate counterclockwise. Because they are locked 90 degrees apart, the current vector always arrives at the vertical axis exactly 1/4 of a turn earlier than the voltage vector. If we track the height of these rotating arrows and stretch them out along a horizontal axis over time, they draw the exact offset sine waves we just calculated. By treating time as a physical rotation, the phasor diagram acts as a spatial map. It takes the invisible timing difference between voltage and current, making it entirely visible and predictable. Because the capacitor has a physical gap, it naturally limits the amount of current that can flow. But unlike a standard resistor, it does this without acting as a bottleneck that burns off heat. We call this unique property capacitive reactance. This graphic shows how capacitive reactance actually operates in reverse. Its resistance is calculated as 1 divided by the frequency times the capacitance. This means the faster the AC source alternates, the higher the frequency, the smaller the barrier becomes. This behaves entirely differently from inductors, which choke off rapid signals. Capacitors are inherently frequency-friendly. They prefer high-speed signals and allow rapid alternations to pass through almost effortlessly. We can calculate the exact current using a variation of Ohm's law. By simply dividing the peak voltage by our capacitive reactance, we determine the exact amplitude of the current allowed through the circuit. By adjusting either the physical size of the capacitor or the frequency of the power source, engineers use capacitive reactance as a programmable gate. It dictates exactly how much current flows across the gap without generating wasted thermal energy. This lack of wasted heat reveals a strange property regarding power. Instantaneous power is simply the voltage multiplied by the current at any given microsecond. In an AC circuit, this means the power fluctuates rapidly at double the frequency of the source voltage. This graph plots the voltage, the current, and the resulting power wave. Because the current is shifted exactly 90 degrees ahead, the power wave is forced to spend equal amounts of time above and below the zero line. When the power wave is positive, energy is absorbed from the source to build an electric field between the plates. When the wave turns negative, that field collapses and every single joule of energy is pushed directly back into the grid. The electrons are constantly moving back and forth, but because the average power over a full cycle perfectly cancels itself out to zero, no total energy is consumed. Physicists called this specific behavior a wattless current. This zero power property is exactly why capacitors are placed throughout our modern infrastructure. They allow engineers to manipulate the timing of voltage and current phases across vast distances, enabling a steady electrical flow without demanding a permanent energy cost.